Good afternoon, everyone. Let us
Hello,
start.
sir.
Today, we shall discuss about solar radiation, its variability and distribution, which is a part of Chapter 9, Solar Radiation, Heat Balance, and the Temperature. Now, I shall share my screen. So, this is a new chapter of our NCERT textbook, Fundamentals of Physical Geography, Chapter 9, Solar radiation, heat balance, and temperature. Can you see my screen, boys and girls?
Yes, sir.
Okay. See, we know that we receive energy from the sun, and because of that, uh, we can survive. And the earth receives almost all of its energy from the sun, and the earth in turn radiates back to the space the energy received from the sun. As a result, the earth neither warms up nor does it cool down over a period of time. Thus, the amount of heat received by different parts of the earth is not the same. This variation causes pressure differences in the atmosphere, and this leads to transfer heat from one region to the other by winds. This chapter explains the process of heating and cooling of atmosphere and the resultant temperature distribution over Earth's surface. And now we shall discuss about solar radiation. What do you mean by solar radiation, and why it is varied? Okay, the amount of solar radiation received by us is varied from one place to another place. So let us read here. The Earth's surface receives most of its energy in short wavelengths. You must know that we receive energy in the form of electromagnetic waves from the sun, and most of its energy is in the form of short waves. Okay, waves, you know. Say, for example, this is a wave. Okay, and so what we call it, this is known as crash, and this is known as straw, and the distance between two crash here is known as wavelength. Okay, it is denoted by lambda, and we receive energy from the sun in short wavelengths. Okay, mainly in short wavelengths, and the energy received by the earth is known as incoming solar radiation, which is in short term as insolation. Okay, actually, insolation is a contraction form of incoming solar radiation. Just see here we have here incoming solar radiation. Okay, and radiation, so contraction. So this word insolation is a contraction form of incoming solar radiation, And the insolation refers to the amount of energy received from the sun by the earth. Okay, and as the earth is a geoid resembling a sphere, the sun's rays fall obliquely at the top of the atmosphere, and the earth intercepts a very small portion of of the sun's energy. You know, the shape of the earth is oblate spheroid. We call it geoid. Okay, that means flattened at the poles. Thus, it is like this. It is like this. So this shape is what we call geoid. Okay, that is flattened at the poles here. Just here, this is the equator. Okay, and so these are the poles. So these are the poles, and let us say here we have sun, and see, this is the atmosphere. Let us say, and here the sun's rays here at the top of the atmosphere is fallen obliquely. That is not vertical in most of the places. Okay, it is oblique here. That is the point mentioned in the book. Okay, just here the sun's rays fall obliquely at the top of the atmosphere, and the earth intercepts a very small portion of the sun's energy. It is said that the earth receives only 1 by 2000 million of the sun's energy. Okay, only a part of the 2000 millionth of the sun's energy. On average, the earth receives 1.94 calories per square kilometer, per square centimeter per minute at the top of its atmosphere. So the energy received at the top of the atmosphere here. Okay, let us say this is the top of the atmosphere, and the energy received here, okay, is only 1.94 calories per square centimeter per minute. And this is what we call solar constant. Solar constant. Okay, this value is also known as solar constant. The solar output received at the top of the atmosphere varies slightly in a year due to variations in the distance between the earth and the sun. See, during the day or during the say a year, or between the seasons, we find variation in the amount of solar radiation received by the earth. So one of the causes for the variation of the amount of solar energy received by the earth is because of distance between the earth and the sun. So during its revolution around the sun, the earth is the farthest from the sun, that is about 152 million kilometers on 4th July. And this position of the earth is known as aphelion. Again, on 3rd January, the earth is the nearest to the sun, that is about 147 million kilometers. That is the distance between the sun and the earth is about 147 million kilometers. And this position of the sun and earth is known as perihelion. Therefore, the annual insolation received by the earth on 3rd January is slightly more than the amount of energy received on the 4th July. Okay, as you will see here, just see here. Here this position, okay, so here this is the sun and this is our earth, and on 3rd or 4th July, okay, the distance between the Earth and the Sun is the farthest. So it is about 152 or 56 million kilometer, and this position of the Earth and the Sun is known as aphelion. And in the other case, on 3rd January here, the distance between the Earth and the Sun is the shortest, and this is about 147 million kilometer, and this position is known as perihelion. And because of these differences in the distance between the Sun and the Earth, the amount of energy received on this day is a little higher than this day. However, due to inclination of the Earth's axis towards the Sun or away from the Sun, it is compensated. Okay, that will be discussed later. Up to here, any question, boys and girls? Do you have any question, boys and girls?
No, sir.
Okay. You must know that solar radiation refers to the amount of energy received by the Earth from the Sun. It is also known as insolation, which is a contraction form of incoming solar radiation. Okay, now let us discuss about the variability of insolation at the surface of the Earth. The amount and the intensity of insolation vary during the day, in a season, in a year, as we discussed earlier. The factors that cause these variations in insolation are here. Okay, number one, rotation of the Earth on its axis. Very simple. Okay, very simple. Here we know that so this is the Earth and this is the axis, and see here the Earth is rotating on its own axis, and that is why, let us say, here we have the Sun, and this side of the Earth, okay, will receive the sunlight, and on the other side, see here on this side, it will be in the darkness. That is this side will be nighttime, and this side will be daytime. So here we get the insolation, and here on this side we don't get the incoming solar radiation. So due to this rotation of the Earth on its axis, there is variation in the amount of insolation received by the Earth. That is number one. Okay, number one factor. Due to rotation of the Earth on its axis, there is variation in the amount of insolation received by the Earth. Another factor is that the angle of inclination of the sun's rays. See here. So let us analyze one diagram here. Okay, just see here. And see, so here this is the Earth, okay, and this is the atmosphere, and we know that our Earth axis is inclined like this, and because of this inclination, okay, see here in this case, let us say here we have the sun. The sun is here, okay, and this is the case of the vertical ray, and in this case here, this is let us say this is a plane surface, and the angle formed here is 90 degree, and so this is for the case of these inclined rays, and let us say this is a tangent, and angle formed here is less than 90 degree. Okay, so in the case of oblique rays or inclined rays, okay, the surface area coverage is more here, as you see here. the inclined rays cover a greater area as compared to the vertical rays of the sun. And that is why heat is concentrated here in a small area in the case of vertical rays as compared to the inclined rays. So in the case of inclined rays here, so this is the case of inclined rays. Okay, in the case of inclined rays, heat is distributed over a greater area, and hence it is cool. So in this way, due to inclination of the these sun's rays on the surface of the earth, there is variation in the amount of insolation received by the earth. Okay, and another factor is that the length of the day. The length of the day here. Let us see another diagram here. Okay, another diagram. Here, this is the case. And here you must know that here we have the sun here in the middle. Okay, here we have the sun in the middle, and you must know that this is the axis. Okay, our axis is inclined in this way. Let us say this is a vertical plane, and the angle of inclination here, I mean our axis is inclined at that angle of this 23.5 degree from the vertical plane, or it is inclined about 66.5 degree to the orbital plane. And because of this inclination of the earth axis towards the sun or away from the sun, we have seasons in the year. And because of this inclination of the earth axis, okay, so we have this variation in the duration of the daytime and the nighttime. See this, let us say this is the position of the sun on this June 21 or 22, and this position of the earth is known as summer solstice. So on this day, the sun's ray is vertical at this tropic of Cancer here. This is what? This is tropic of Cancer, that is 23.5 degree north. This is what? This is equator, and this is tropic of Capricorn, that is 23.5 degree south. Okay, so on June 21 or 22, the sun's ray will be vertical here at the tropic of Cancer. And on this day, in the northern hemisphere, the daytime will be the longest, and on the other hand, the nighttime will be the shortest on this day in the northern hemisphere. Alternatively, here in the southern hemisphere, the duration of the nighttime here, will be the longest, and the duration of the daytime here will be the shortest on this day. Okay, and this is another condition. Okay, this is what I call winter solstice. It occurs on December 21 or 22. So on this day, here the sun's ray is vertical here, say on the tropic of Capricorn, that is 23.5 degree south. So on the day of winter solstice, that is on 21 or 22 December, the sun's ray is vertical on the tropic of Capricorn. And on this day, okay, the daytime will be the longest in the southern hemisphere, and the nighttime will be the shortest on this day. And here again in the northern hemisphere here, on the day of this winter solstice, nighttime will be the longest, and the daytime will be the shortest. So this is another condition, and these two position is known as equinoxes, that is equal night. Equinox means equal nights. Okay, that is the night time and the daytime is equal. It may be 2 hours daytime and 12 hours nighttime. Okay, so it occurs on the day of this March 21, 22. On this day, the daytime and nighttime is equal, and another position is here that is known as autumn equinox. This is known as vernal equinox or the spring equinox. This is the case of autumn equinox. It occurs on September 22, 23. On this day also, there is equal daytime and nighttime, because at this position there is no inclination of the axis towards the sun or away from the sun. So in this way, the length of the day, okay, determine the amount of insolation received by the earth. Up to here, any question, boys and girls? Do you have any question? Boys and girls, do you have questions?
No, sir.
Okay. So another factor here is transparency of the atmosphere. In the previous chapter, we learned that the atmosphere contains lots of dust particles. Okay, and if there is lot of dust particles in the atmosphere, then we receive less amount of insolation, less amount of solar radiation. Just you may observe in the month of this January, February, okay, due to dust particles and the other particles in the atmosphere, we receive say less amount of insolation in addition to the inclination of the sun's rays. Okay, that means if the atmosphere is very clear, clean and clear, then we receive bright sunshine. And if the atmosphere is dirty, if it contains a lot of dust particles, then we receive less amount of solar radiation. So this is another one. And next we have this configuration of lane in terms of its aspect. So this is another factor. So let us consider this case. Let us say this is a mountain range. Okay, this is a mountain range in the northern hemisphere. This is a mountain range in the northern hemisphere. Let us say the mountain range is running east-west direction. Let us say this side is east, this side is west, and that means this side will be the southern side of the mountain. Okay, and this side will be the northern side of the mountain. Then, so if the mountain range is in the northern hemisphere and if it is running in the east-west direction, then here we have the sun. The southern side of the mountain will receive more sunlight than the northern side here. The sun, in the winter season, the sun goes to the south, and because of that, if the mountain runs east-west direction, then the southern side of the mountain will receive more sunshine, that is more amount of insolation, as you see here, and that means this side of the mountain will get vertical rays, and the other side, that is the northern side, will get oblique rays, that is the inclined rays. So in this way, due to the aspect, due to the direction of the slope of the landforms, the amount of insolation received by our earth is different. Okay, so these are the factors affecting the amount of insolation received by the earth. Okay, and about the why do the amount of insolation received differs from place to place is again explained here. And here this is the case of the vertical rays and the inclined rays, and you will see here in this diagram also. See, these are the sun's rays, okay, and here the angle of inclination is 90 degree, and as you move away towards the pole it is less than 90 degree, okay, and that is why here the amount of insolation is less as compared to the tropical regions. And whatever we have explained earlier is also mentioned here. See, the area covered by the vertical rays is always less than the slant rays. If more area is covered, the energy gets distributed and the net energy received per unit area decreases. Moreover, slant rays are required to pass through greater depth of the atmosphere. That we have already explained using this diagram. Okay, so using this diagram we have already explained. Inclined rays cover a greater area than the vertical rays, and that is why heat is concentrated in the case of vertical rays and we feel hot. Next, we have the passes of solar radiation through the atmosphere. Actually, this factor also we have already discussed, but let us read again. The atmosphere is largely transparent to short wave solar radiation. That means this short wave solar radiation can pass through easily the atmosphere and hit on the surface of the earth, and the incoming solar radiation passes through the atmosphere before striking the earth's surface. Within the troposphere we have this water vapor, ozone and other gases absorb much of the near infrared radiation. This is what I call greenhouse effect. In the previous chapter we have learned about it. Okay, we have learned about it, greenhouse effect. So let me explain you again. Let us say this is the surface of the earth, and here we have the sun. The sun radiates energy in the form of short wave. Okay, these are short waves, and these short waves will be the sunlight, you know, in simple terms. Okay, the sunlight will be absorbed by the surface of the earth, and the surface of the earth will be heated. Again, the heated earth will radiate back long wave terrestrial radiation. It is also known as infrared radiation. Okay, it is also known as terrestrial radiation or infrared radiation, and these radiations are absorbed by the dust particles, then by the water vapor, okay, then by the these methane, and then by carbon dioxide, and these gases absorb the infrared radiation released by the surface of the earth, thus warming the earth's atmosphere, and this is known as greenhouse effect. Okay, and it is because of the greenhouse effect that we can live comfortably even in the nighttime also, and in the in the houses also. So this is a very useful phenomenon. And very small suspended particles in the troposphere scatter visible spectrum both to space and towards the earth surface. This process adds color to the sky. I think you will see that the color of the sky is blue in the daytime. At the same time, see the red color, then the rising of the rising and the setting sun, and the blue color of the sky are the result of the scattering of the light within the atmosphere. That means say during the daytime when the night is very clear, then the color of the sky is blue. Then at the time of sunrise and the sunset, at the horizon we see orange to reddish color sky. All these are the result of scattering process. Then what do you mean by scattering? Actually, see, we have learned that the atmosphere contains dust particles and gas molecules, and these dust particles and the gas molecules, okay, scatter. So, for example, this is a ray of sunlight, and this will scatter. These gas molecules will scatter the light in different directions. Just see here. This is the electromagnetic spectrum, and see here. Uh, just see here. On this side, we have the shorter wavelengths like gamma rays, X-rays, ultraviolet, and on this side here we have the longer wavelengths like radio waves, television waves, then microwaves, infrared. So in between these two, here we have the visible portion. Okay, and in the visible portion also, we have 7 colors. You know that we have violet, indigo, blue, green, yellow, orange, and red. So within the visible portion also, here the violet ray has the shortest wavelength, whereas the red light has the longest wavelength. Okay, that means the wavelength becomes shorter on this side. And see, and we have one more diagram. Okay, and these colors, we have learned that the sunlight contains 7 colors, and these out of these 7 colors, violet, indigo have the shortest wavelength, and uh, then red, orange has the longest wavelength. And see, what is going on in the atmosphere is that the gas molecules scatter these shorter wavelengths like violet and indigo, and that type of scattering is known as this relay scattering, and this is how scattering is taken place by the gas molecules, and it is very effective when we see the sky okay, overhead. See here, from overhead the real light scattering is dominant, and the other scattering type, this is what I call my scattering. So it is caused by the bigger particles, okay, mainly by the dust particles, and uh, you must know that the real light scattering strongly favors the short wavelengths, and that is why we see the blue color of the sky. That means gas molecules more effectively scatter blue and violet light that have shorter wavelengths than they scatter red and orange, and this accounts for the blue color of the sky. This real scattering accounts for the blue color of the sky, because real scattering favors the scattering of the shorter wavelengths of these violet and blue color by the gas molecules. Conversely, the sun appears to have an orange to reddish hue when viewed near horizon. And this is the result of the great distance solar radiation must travel through the atmosphere before it reaches our eyes. During its travel, most of the blue and violet wavelengths are scattered out by the atmosphere, okay, by the atmospheric these dust particles and molecules, gas molecules. Consequently, the light that reaches our eyes consists mostly of red and oranges. The reddish appearance of clouds during sunrise and sunset also results because clouds are illuminated by the light from which the blue color has been removed by scattering process. See, this is the art, and uh, see, when the sun is at the horizon, the sun's rays travel a greater distance here. So let us say this is the case, greater distance here. And when the sun's rays travel a greater distance in the atmosphere, due to the scattering process, okay, blue and violet rays are almost removed from the sunlight, and thus remaining these red and oranges, okay, in the light. And that is why in the sunset and in the sunrise hours we see this reddish color of the sky. Any question, boys and girls?
No, sir.
Okay, the last part, see about the spatial distribution of insolation at the Earth's surface. We have learned that there is variation in the amount of insolation received by the Earth from place to place. The insolation received at the surface varies from 320 watt per square meter in the tropics to about 70 watt per square meter at the poles. That means we get more amount of solar energy at the tropical areas as compared to the polar areas. So maximum uh, insolation is received over the tropical deserts. Okay, over the desert areas we get maximum amount of insolation, that is incoming solar radiation, where the cloudiness is the least. Over the tropical desert, cloudiness is the least. That is, the sky is very clear. Equator receives comparatively less insolation than the tropics because over the equator there is cloudiness almost year round, because equator receives heavy amount rainfall, and that is why the sky is not clear. The sky is mostly covered by clouds, and that is why equator receives less amount of solar radiation as compared to tropics. Okay. Generally, at the same latitude, the insolation is more over the continent than over the ocean. Over the same latitude also, just see here, and these are the latitude. So over the same latitude here, let us say this is the continental area and this is oceanic area. Over the same latitude here also, let us say this is 45° north. Over the same latitude also, we get more sunlight over the continents as compared to the oceans due to cloudiness. In winter, and the middle and the higher latitudes receive less radiation than summer, because in winter the sky is covered with fogs, high fogs, and perhaps due to that condition we get less amount of the solar radiation here. Up to here, any question, boys and girls? Any question?
No.
Okay, then, if you don't have questions, let us stop here for today. Thank you very much for joining my class.